Good morning, everyone. My name is Suji Choi. I'm postdoc at Harvard University. Um, Before I start, I would like to give thanks my supervisor, Professor Kip Parker, and my lab mate. And then while I am in Germany, I would like to give a special thanks to Professor Andreas Bausch, who support this research. So the heart is a muscular organ that pumps the blood throughout our body. So it is not only like contract and relax during the cycle, there are more coordinated function related to make the efficient pumping. For example, like cardiac tissue has a very hierarchical structure within this 3D chamber-shaped ventricle or atrium, and this ventricle or atrium has a coordinated motion so that they pumps the blood efficiently. And there is a valve between those atriums and valve so that this allows directional flow control so that the blood circulation is occurred in one direction. So to study heart or cardiac physiology or to conduct drug test as a clinical test, a microphysiological system should include the cardiac model that represent the physiological relevant function of the heart from the cell model or tissue model. So for this microphysiological system, there are multi-scale cardiac model, including isolated single cell pattern to the 2D model, 2D laminar tissue, and then there is a 3D ventricle model. So to build this cardiac model, we need to think about how this heart is formed. So in the heart, there is a hierarchical organized structure. So when we look at it closely, there is an anisotropic extracellular matrix, fibrous shaped network. So this provides a structural integrity to the heart. And then along these ECM fibers, there are the cardiomyocytes aligned along this fiber, and they are interconnected through this cell junction, so they communicating each other, and then so that when the myofilament inside the cardiomyocytes works to generate the force, contractile force, they shows the synchronous contraction of the tissue so that they provide the efficient pumping. And when we think about the ECM organization during heart development, you can see here in the early stage of the heart development, the cardiomyocytes are less organized, and the ECM is still secreted by fibroblasts. And then when it gets all matured and later stage, the cardiomyocytes are aligned, and then along this anisotropic ECM matrix. So based on this ECM organization during heart development, we can incorporate this into this to build an in vitro heart model. So one way is we can culture the cardiomyocyte with the fibroblasts and ECM materials so that the fibroblasts secrete the ECM material to support the structural integrity, as well as the cardiomyocyte itself self-organize into this cardiac tissue model. On the other hand, we can, our body in others' heart has an anisotropic fiber structure, we can provide this microstructure to guide the cell's alignment. So here, if we culture the cells on top of this microstructure, like a microgroove structure or fiber structure, we can achieve this anisotropic cardiac muscle structure. And when we move on to the organ level cardiac tissue, we can also use cell and matrix to print into this 3D construct, or we can print the matrix into the 3D shape and then culture or deposit the cells on top of this, around this organ-shaped matrix. And here, but above all, the most critical important step to build in vitro model of the heart is to recapitulate the structure and function of the heart. And to do that, we need to provide the extracellular structure cue to form this anisotropic syncytium. So in my research, to build a 3D in vitro model of the heart with the cellular alignment, I had two goals to wanted to achieve. So first one is I want to get this 3D structure with the organ shape or with the accurate shape of the ventricle. And second goal is I want to provide the structural cues so that the cells can be aligned within with the scaffolds. So the idea we were thinking of is we can print the ventricle chambers like this, but we can still incorporate the fiber structure so that as the fiber structure aligned around these scaffolds, so then this microstructure can guide the cell alignment. So what we use is we use the gelatin fibers. So in our lab, we have a focus rotary jet spinning to spin these fibers. So you can simply imagine cotton candy machine. So you can get the cotton candy from the sugar solution. So instead of sugar solution, we use the gelatin solution, and we also use the air blow so that we can collect the gelatin fiber into like fabric shape. And then we can embed this fabric into the gelatin, in an ink type. So we fragment this fiber into lengths of 100 micrometer, so that this is the image of the fragmented gelatin fibers, and they are well dispersed in the PBS solution. And then we mix these fibers into this gelatin and alginate hydrogel. So these gelatin and alginate, this hydrogel provide the structural integrity between this fiber structure and also allows for the ink extrusion. And then this fiber later, when they get aligned along the in the scaffold, they provide the structural cue to the cells. But not only the structural cue, the fiber itself also improves this 3D printability. So you can see here, when there is no fiber, it shows very liquid behavior. But when there is fiber, you can see this filament is formed continuously, so that this allows to make the nice shape of the 3D structure. So here, when there's no fiber, this donut shape with the mesh infused structure has no similar structure, but we can layer it up and then print this mesh structure using this fiber infused gel ink. Now I call this ink as fig ink. So now we want to print this 3D ventricle structure. So ventricle structure looks like a chamber, a cone shape. So we take these coordinates, 3 XYZ coordinates to make this cone shape, 3D cone shape, and we make it upside down, and then we rearrange these coordinates into the order of the printing direction. Then we can make the G-code, which is the language to control the 3D printer, so that we can print this ventricle structure without using any supporting material, but they are very stable and very similar structure as it designed. And not only this ventricle structure, we can also make more complicated heart components, including valve and dual chamber ventricles. And we can also control the angle by making G-code, so that we can replicate the multiple direction of the muscle within this heart. So this is printed in an angled way. And now we print this scaffold, and then we wonder how these fibers arrange within this scaffold. So we control the fiber concentration from 5 to 10, and then what we see is as the fiber concentration increase, they become very they are more tends to the solidify quickly after it printed out. So this solidifying the gel is maintaining this shear induced fiber alignment, so that after we print it out, you can see this analysis image and the SEM images shows that the fibers are well aligned because of the shear stress aligned fiber. And then now we wonder if we culture cells on top of this structure, how this cell behave on top of this scaffold. So to check the effect of the fiber, we culture the cells on top of the gelatin alginate substrate without fiber, and then we use the fig ink to print the 2D structure. And then we culture these, here we neonodal red ventricle myocardium, and then when we culture the myocyte, this without the fiber, they randomly distributed and connected a random distribution. But here, when you have this fiber, it shows very nicely aligned cardiomyocyte. And so I wanted to show this video, but it's not playing. Oh, the movie stops, unfortunately. So this one showing this electrical physiological propagation on top of this tissue. So because it has no alignment of the tissue, the electrical propagation occurs in an isotropic propagation, whereas when there is fiber, the electrical propagation occurs faster in a printing direction compared to the transverse direction. So by showing this this electrical physiological coupling between the cardiomyocyte, we wonder how this contractility depending on the direction control. So here we print this scaffold with 3 different directions. One is parallel to the longitudinal angle to the long axis, and then perpendicular to the long axis. And after we culture the cells, we delaminate this whole structure from the substrate. Then what happens is, because cell wants to contract in one direction, they shrink, but the other parts there is no cell, so the dimension is maintained. So they want to bend inward. So what happens is, because it has a long tissues, they want to roll up, and then when they are angled, the bending becomes twisting, and then when they are this direction, perpendicular direction, the bending becomes folding motion. So now here we can see the preferential electromechanical coupling of the cardiomyocytes occurred in the printing direction, so that it shows distinct contractile pattern depending on this printing direction. Oh, now it plays. And then we want to we build the 3D in vitro ventricle model. So after we printed the scaffold, we cultured the stem cell cardiomyocyte on top of this 3D ventricle. And then we can see these cardiomyocytes are nicely organized along the printing direction. And then we also measure this calcium propagation so that this calcium propagation occurs around this ventricle, so that it shows unidirectional propagation. So we see this structure function recapitulation, and then we wonder how this ventricle is pumping, contracting. And this one is, we after we culture the ventricle, we put the fluorescence beads on top of the ventricle, and we track this beads movement. And then when we map these beads movement, you can see this, the ventricle is well contractile, entire structures are moving. And we also, the video stopped. So we want to also see the contraction of I have to click. So here you can slowly see the beads movement around the ventricle. So we put the fluorescence beads around the ventricle. So because of the cyclic contraction, the beads are moving, when it's contract, when the beads are moving from inside to outside the beads, and when they relax, the beads are coming inward again. So like this. And then when we then we can calculate this using this beads movement. We can calculate the mass flux change during this ventricular contraction. And oops, I clicked too much. So, oh no, it's moving. And so then this cyclic movement, we can see this sinus movement in times because of the liquid around the ventricle, and we can measure the volume change of the ventricle. So then this gives a 5% of volume change. This is very quite low volume change compared to our heart, but this is still like considering this ventricle is very smaller than our real heart, we still can provide this physiological relevant cardiac function from this in vitro model, the in vitro ventricle model. So this is summary slides. So for the microphysiological system, we need different kinds of multi-scale cardiac model. Well, now here we want to focus on the 3D ventricle model. So here we provide the scaffolds that both macro-scale geometry and the micro-scale align the structure simultaneously, so that we can, when we culture the cells, it provides the self-organization of cardiomyocyte into the functional syncytium, so we can observe, so that we can observe the structure and functional function of recapitulation of the heart. Thank you for listening my talk.
Thanks, Suji. We have time only for one short, quick question.
So, hi, thank you very much for the very nice talk. I was wondering, so have you tried different stiffness of your gel and different concentrations of fibers, and how does that impact the tissue formation and its contraction?
Actually, I didn't go detail about how I control the stiffness, but here, after I printed, we need to cross-link this ventricular structure. We used microbial, we used an enzyme cross-linking method, and then we can control the enzyme concentration so that we can control stiffness.
I think we need to move ahead with the next talks. Thank you very much, Suji, for the nice talk.